Welcome to a series of pre-cal videos that I'll be making this year. I'll be teaching pre-cal for the first time. Pretty excited about it. I just want to go over a couple of tidbits before we get started. The first is that we're in an accelerated course, so we do the entire course all the way through December, and it moves pretty quick. So these videos will help you, especially if you're going to be absent, but keep in mind the videos are going to be short and to the point, and the notes on Canvas are going to be crucial. You don't want to show up to class and ask me, what did we do yesterday? You should come in and know exactly what we did, go over the notes, and even attempt the work. Alrighty, so here's Unit 1. It's basically a review of algebra. And we broke up Unit 1 in two parts. As you can see, the first 2 weeks of school are just basic algebra review. And then we're going to have a short test over that, and then move on to some more algebra review. And then we'll start getting into more traditional pre-cal content. It is vital that you do all work and don't skip a single day if all possible, even though that's near impossible to do because y'all are pretty busy. You got sports, all kinds of activities going on. So let's go ahead and get to it. And what I'm going to do is go over Tuesday's lesson. Wait a second, Wednesday's, yes. I just did the calendar. Let me show you the calendar real quick. This video is going to be a little bit longer than some others. But here we are. We're going to have first day just going to be algebra review. And I'm going to send out an email a couple of weeks before school to encourage you all to get a head start on that if you were weak in your algebra. There's not much room for spending time to go over remedial work in this course. As you can see, the first unit, 1A and 1B, is largely a lot of algebra. And even Unit 2, we're going to get into Algebra 2 concepts. We're going to put a little twist on it. We're going to start looking into some more characteristics of quadratics and some other things. And moving on, we get into, again, a lot of stuff you're going to recognize in your previous algebra courses and geometry. If you're in honors geometry, a lot of this is going to be very familiar to you. If you came from on level, some of it will be quite new, such as law signs, cosines, so on. Unit circle, again, depends on what your previous geometry experience was. It may be familiar, it may be brand new, but that's not too complicated. But the trig identity should be new to most people. And we're going to dive into that really in depth. It's going to be pretty good, because that's a foundation for calculus. Remember, pre-cal, even in the state requirements, it says right up front, pre-cal is taken to prepare you for calculus, and that's exactly what we're going to be doing. And then moving on down, we get into some various other things. We'll get into binomial theorem, which is a big deal, and then some conic sections to end it off with parametric equations. As you can see, there isn't any fluff time. We're very, very busy on this calendar. Okay, so let's get moving on. Again, largely a review. So what we're going to do is, first of all, we need to be very comfortable with domain and range and interval set notation. And it depends on your previous teachers. A lot of previous teachers did interval notations. It's very common. You're going to see that at the high school and college level courses because it's easy. Interval notations is basically that. When we do our domain and we go from -4 to 4, it looks like a continuous function here. This is open circle, so we don't include that. So we're going to annotate that with a parentheses, and we're going to have -4, and it's going to go all the way to 4, but that is inclusive, so we're going to show inclusiveness by using that bracket right there. And of course, the range going from low to high, we go from -3 to 0.5, so we go -3 to 0.5. Okay, that's a comma. And it's been a while since I've done videos, so this writing tablet I'm just not quite used to again. Set notation is a big deal in mathematics, and we're going to practice set notation frequently. So when we do set notation, when we talk about domain, we're going to call it as a set of all x's such that x is between -4 and 4. So we're going to have -4, not inclusive, x, and inclusive 4, and close the set. So this reads, for all x's such that, this little line means such that, x is between -4 and 4, with this being inclusive. That's not inclusive. And of course, our range could be written very similar. We're going from -3 to 5, and it's going to be all y such that it doesn't include 3, but it's greater than 3 and less than or equal to 0.5. All right, so let's go on to the next one. So here we have another continuous relationship, continuous function. We'll talk about function yes or no in a second. And we have an open circle here. And using interval notation, we're going to go from left to right on our x's, small to big. And that's going to be -6. And it's going to go to infinity. Well, we can't include infinity because there's a lot of mathematical debate on, well, it's almost a philosophy course on what infinity is. So that's what our domain would look like. And of course, our range will be all y's. We usually go from small to big. So little counterintuitive here, we're going to have negative infinity. And you're going to go all the way up to 5, not inclusive. Would it be counted wrong if you did 5 to negative infinity? Well, mathematically, you can make the argument that they're equivalent statements. So no, I wouldn't do that. But it's just bad form. Okay, so set notation, I'll just do the domain. It's going to be all x's such that x is greater than 6, but not inclusive, and goes all the way through infinity. Okay? All right, moving on. Now we're going to take a look at whether things are functional or not. Again, this should be reviewed. Many of you learned the vertical line test, where you would just go / / vertical lines. But the definition behind that is what's important. Basically, a function is a special type of relationship that for every x or every input, there's one and only one y. There's one unique output. Now let's take a look at this example here. Here we have 1 as our input and output is 4. And we have 3 as our input, output is 4. They have the same output, but these are unique in that for every 3, there's only one y, and that's going to be 4. So this, of course, would be a function. The same thing here. For every x here, there's only one output up here. So this x over here, there's only one output down here. So yes, that would be a function also. The vertical line test would be you take a vertical line, and if it passes through the function only at one point, it's a function. Here, this fails the vertical line test. Have function here. But take this x right here, you have 2 y's. So this would be a no. This one would be yes. And this would be discontinuous because we're going along here on a nice continuous path. My domain stops right here, and my domain picks up again right here. So this would be a discontinuous function. Discrete, and what do we got here? We got 3 going into a 7 and a 3 going into -2. So if I were to write this like this, you would see something like this, 3 going into a 7 and a -2. Well, the x's repeat. So that would not be a function. So to determine if these are relationships are a function, well, you can quickly see that this is going to be a quadratic. And there's 9 up here with my vertex on the y-axis. So it's going to open up down like this. And yes, that's going to be a function. And we can do a little table. We could do a test. We could put in 0 in here, and we're going to find a unique y. We could put in 3 in here. We're going to find a unique y. So on. Because here's my x's, there's my unique y. Let's jump over to this one, though. So let's go ahead and solve for y on this one. So when we do this, we're going to have y squared is equal to -x plus 11. And you have y is equal to plus or minus, we're going to take both roots of -x plus 11. So what's going on here is if you actually do a table, now we realize real quick that x can't be, if we're going to stick in the real number system, x is not going to be greater than 11. Can't be, it can equal to 11, but it's not going to be greater than 11. Because then we have a domain problem. We're going to be looking into complex numbers here. So what we're going to have to do, this is a terrible graph. We're going to have something that going to look like this. Okay, and right here is 11. So what we have here, I could pick any x, say pick 0, and I'm going to have square root 11 plus or minus. So we have plus or minus 11 if we let x equal to 0. And so for every 0, we have a positive 3 point something and a negative 3 point something. So this one is not going to be a function. Oh, this, by the way, is continuous. Sorry, we're supposed to put that in there. Okay. Here we obviously have a discrete because discrete, if you recognize, will be like dots or something like that. So yes, it's going to turn out to be a pretty straightforward function. When we put in -3 into here, you're going to get -313. All right. So let's get back to my pen. Y is equal to 2, -3 squared minus 5 is equal to 13. When you do y is equal to 2, 1 squared minus 5, you're going to get -3. And when you do y is equal to 2 function of 5 minus 5, let's see, squared, make sure that's going to be 50, 45. All right. So my y is going to be the sets of my domain, my range right there. Okay. And I could write that as set notation or whatever, and be all y such that y is equal to -3, 13, and 45. So this is a very interesting one. So this is discrete, okay? Because we have 3 distinct points here for my range. Now here we have y is equal to 1 over x minus 2. First thing that I notice here, let me go ahead and do this in a different color, is that if I put in 2 here in the domain, I'm going to get 1 divided by 0, which is a contradiction in mathematics. So we know that we're going to have a domain restriction for x does not equal to 0. So that's going to be a domain restriction right there. But otherwise, x could be any other number. So what we have is a graph that looks like this. I better do a little bit of do this instead. That might be a little bit easier. And what I have is a graph to where, imagine this, x gets to be very, very small. -20, -30, -40. This is going to get very close to this right here, our y equals 0 line. If x got really, really big, it's going to remain positive, but it's going to be a very small fraction. It's going to get over here. But what we have is we can't have x equal to 2. So I would have a dashed line where x cannot equal to 2. Okay? And a graph that would simply look something like this. It would come very close to there and come down. Oh, I missed it by a lot. Okay? Come down like this. And then I have a graph that comes down here, very close, and comes this way. Okay? So that would be a function, but it's discontinuous. That would be a discontinuous function. Alrighty, so that is it for today. I'll go ahead and get this uploaded to YouTube, and most of my videos are going to be much, much shorter. Alrighty.